So we're starting chapter 7, circular motion. I'm going to do a stopper on a string demo real quick. That's just where I take my stopper on a string and I whirl it around in a circle. Okay, awesome. No, I'm not going to let it go. Not yet anyways, okay? So we're going to talk about circular motion or angular motion, as we're going to call it, versus linear motion. Okay, now linear motion has been where it's either moving the x-axis or it's moving in the y-axis, okay? Or we even had 2D linear motion where we're a projectile. We're going through both axes at the same time, okay? Linear motion is also called translational motion. So let's write that down, okay? Somewhere on your paper, we can say that linear motion is translational motion. Okay? Yeah, that's better. Okay. All right, so let's see here. If I'm going to swing this stopper around, okay, let's talk about the stopper when it's right here. We're going to zoom into the circular motion, kind of slow it down, okay? So the stopper starts out here, and then it moves up to here in some amount of time, okay? Did the x-coordinate of the stopper's position change with respect to time? Did it change from here to here? Yeah. So the x position of the stopper was at this point, and I moved it here. Now it is this far away instead of that far away from the origin. Does that make sense? So it actually, the x distance shrank, right? Okay, now let's talk about the y position. So this is position A, this is position B. Did the y position of the stopper change with respect to time? Yes, it did. So that means that both x and y positions changed over time. That's going to make it really difficult if we want to do any calculations because we have two variables changing at the same time. Correct? Okay, so let's write down what that looks like on the Cartesian coordinate system. What is that, the Cartesian coordinate system? Anybody know? That is the standard coordinate system that you've been using since middle school, okay? So that's your regular old x and y axis, okay? All right, so let's say we've got our origin point, then we've got our stopper out here, okay? All right, and then we've got x and y positions, okay? All right, so if we aren't using the x and y coordinate, and by the way, I guess I'll put that up here, our ordered pairs then would, of course, be x and y at that position of the stopper, okay? So if we're not going to use the Cartesian coordinate system, does anybody know what the name of the other coordinate system is? Anybody gotten that far yet in pre-cal? No, it starts with a P. No, it's the polar coordinate system. Have y'all heard of that before? No? Okay. All right then. So let's answer these questions here. We said yes, that the stopper's x position changed over time, and we said yes, the stopper's y position changed over time. Everybody get everything written down on this screen? Now that picture up there at the top, wherever, you don't really need to worry about that just yet. No. We're going to talk about all of those things over the course of this. But you don't have to draw that picture just yet. Mm-hmm. That's right. Yeah.
And that's acceleration and velocity. What else do you want to know?
All right. Are we good? Yep. Okay, so let's look at the next piece then. We're going to use the polar coordinate system. We're going to change our Cartesian coordinate system, the x and y coordinates, into these polar coordinates. Okay, so we're going to do that with our right triangle trigonometry. Now what we're doing here is a best estimate, okay? It's not really going to be exact because when that stopper is going around the circle, it's actually in an arc, right? It's not doing a perfect triangle as what I'm drawing here. So it's going to be a little bit different. But we're going to say that it is definitely making an angle, okay? Between any two positions on that arc, there's an angle between the two positions. Does that make sense to everybody? Okay? And we know that from the origin point out to where the stopper is, that qualifies as the radius of the circle. Everybody okay with that? Mm-hmm. Which means that on the polar coordinate system, our ordered pairs are going to be r and theta instead of x and y. So let's look and see what changes then if we use the polar coordinate system, all right? So if this is position A of the stopper, and then I rotate it up to position B, let's ask the same questions now. Does the angle theta change from position A to position B?
Yes.
Yeah, the angle does change, okay? So write that question and answer down, just like we did for the X and the Y one previously. Write down the question, does the angle theta change over time? And the answer to that question would be yes. Theta. Okay, now let's ask another question. Okay, so from position A to position B here, does the radius change? No, the radius does not change. So write that question down and that answer. Does the radius change over time? And the answer would be no. Okay, so do you see how that's beneficial? By switching to the polar coordinate system, we now have only one variable changing at a time. The other one will remain constant. So won't that be helpful to us when we're trying to do calculations? Yeah, so that's why we're having to do that, why we're switching coordinate systems, okay? So now let's talk about how we're going to relate those two coordinate systems. This, we're going to say, is a right triangle. Now that's true if you're moving very short distances on the arc. Okay, so for example, if you know, our rubber stopper was here, and then it's going to travel just a very short amount and be down here at this new location, then this arc, this curve here, is going to be more and more like a straight line the closer and closer position A and B are to each other. Does that make sense to everybody? If you let it go a really large distance, then the arc becomes more pronounced. You can definitely tell it's a curve. But if we only moved a very short amount of space, then it becomes more and more like a straight line, and then we can approximate it as a triangle more easily. Is everybody with me on that? Okay, so again, what I'm about to show you here is really only true for very short distances or changes in position, okay? All right, so we're going to use our right triangle stuff. If this is the X position and that's the Y position, somebody raise your hand and tell me, how can I find the Y position or the Y length? Yeah? Very good, okay? So we're going to be able to say then that the sine of theta is equal to the opposite side over the hypotenuse, right? So the opposite side we're calling side y, Now, what's the hypotenuse of this r? The radius, okay? That means that side y is equal to the radius times the sine of theta. That's a boxed equation. All boxed equations from now on will be given to you on a formula chart that you'll receive here pretty soon on any quiz or test. You'll have that formula chart available to you. If I do not box the equation, you are responsible for memorizing it, okay? Most equations that we get from now on will be boxed equations. Things that I don't box will be additional equations that stemmed from a boxed equation. It will be I will substitute into it and get multiple other equations out of it. But you don't have to know those because you got the boxed equation. And if you can do the substitutions yourself, then you don't need to memorize any extra equations that came from it. Does that make sense to everybody? Okay. All right, so that gives us the y one. Now let's talk about the x one. What can I do to get my side x? Garrett? Cosine. Very good. So the cosine of theta then is equal to the adjacent side, which we're calling side x, over the hypotenuse. What's the hypotenuse? The radius. Very good. So that means that x is equal to the radius times the cosine of theta. This is another boxed equation. Again, this represents a change from linear to polar. Okay? On the left-hand side of both of these equations, we have linear coordinates, x and y. On the right-hand side of both of these equations, we have polar coordinates, r and theta. Everybody see that? So any time from now on that we are switching anything from a linear system or translational system to an angular or rotational system, you will have to use r times theta somehow. There will be a radius and there will be a theta that have to be multiplied by each other in some way. Yes?
So linear is like x, y.
Uh-huh.
Polar is what?
Polar is theta and r, the angle and the radius of the circle. Okay.
Is the coordinate plane still the same though?
For the polar system, and they draw it weird. You get like rings kind of like this, and it's how much out from the ring you go. Okay, out like that. That's kind of like what a polar system looks like. Yes, you may. Okay, so let's talk about pi. We love pi. All right. Pi is an irrational number. That means that it never repeats and it never ends. Okay? I need you to know the first 6 digits. All right, pi to 6 digits. So that's very good. You're fantastic. You've got all 6. Okay. So I always do a little cheer here to help you remember pi to 6 digits. No. I always say sine, cosine, sine, 3.14159. And then, so, yeah. So if you remember that, then you've got pi, all right? Okay. No. So it's 3.14159. Yeah. So it looks like I've not put my little equal sign there. That should say pi is equal to the circumference, capital C, over the diameter, capital D. Okay? So pi is the ratio of a circle's circumference to a circle's diameter. Okay? So pi is the ratio of the circumference to the diameter. Yeah, pi is the ratio of the circumference to the diameter of a circle. Okay. Okay. The circumference is equal to pi times 2 times radius, because the radius, twice the radius is the diameter, right? So all we did just now to get this second bullet was we rearranged the first bullet. Okay? So if I have pi equals c over d, then let's go ahead and multiply by the diameter on both sides. That means the circumference is equal to pi times the diameter. And if the diameter of a circle is equal to 2 times the radius, then we can substitute 2r in where we see d. And that's how we come up with this second bullet here. Circumference equals pi times 2r. Yeah, you should know the formula for circumference. Exactly. Okay, the second and the third bullet are identical to each other. Why am I allowed to put them in different orders like that and it still be the same thing? What? Yeah, what's that property? What's it called? Commutative. Very good. So this is the commutative property. Okay, so because of the commutative property, we know that circumference traditionally is referred to as 2 pi r. Okay? Would someone let Desire in, please? She didn't. Says, would you make sure that Isaac gets those things? Okay, so now let's talk about the units for pi. Yes, pi has units, okay? So if we're looking at that equation for pi, circumference divided by diameter, right? If you were going to measure the circumference of a circle, what unit would you measure it in? Meters, okay? Circumference is the linear distance around a circle, all right? So we would measure that in meters. What would you measure the diameter in? Meters, okay? So that means right here we would have meters divided by meters. And what's something divided by itself? 1. But it's not just 1 in this case. It's going to be radians, 1 radian, okay? So pi's units are radians. What are radians? Okay? Radians are what we call a placeholder or a unitless number, okay? They only belong in the polar coordinate system. If you move out of the polar coordinate system and back into the Cartesian or standard coordinate system, then the radians go away. They have no place there, okay? But if you're in the polar coordinate system, you must write radians. They are an actual unit that you have to have. If you don't write it, it's a naked number, okay? Garrett?
So, say you're doing like circumference 3 divided by diameter, which is equal, that's equal 0.75
Radians, correct. Okay. Siobhan, you had a question?
What about when we graph like the cosine and sine functions and we use radians?
When you switch out of, if you're going back to the Cartesian coordinate system, then radians go away. Now, if you're asking about what mode your calculator has to be in, it doesn't matter. The only time that matters is if you're hitting the sine, cosine, or tangent button on your calculator. If you're not touching those, then it doesn't matter what mode you're in. Okay? Everybody have all of this stuff? Yes? All right. Okay. All right, so conversions that you have to know. All right, and actually it's just this. Yeah, that's really the only one that you absolutely need to know. The other ones are good to know, but if you know the bottom one, then you know the other two, okay? So it's saying that 1 revolution, okay, and by revolution we mean a full trip around the circle, okay? 1 trip around the circle is equal to 2 pi radians. It's also equal to 360 degrees, which means that 2 pi radians is equal to 360 degrees. If you're in pre-cal right now, they're probably having you learn that pi equals 180 degrees. You may not be there yet in that course, but when you get there, that's what they're going to make you know. You already did that? Okay, so you finished that. That's what they told you to remember in there. It will work in this class too. You can do that if you want. I've always used 2 pi radians equals 360 degrees. Well, we will do some practice questions in just a minute, so you'll know. Yeah. Right. No, that is not a boxed equation. No, it's just, yeah, for real. It's just me emphasizing that. I need to be careful about that. Thank you, Adam. Okay. Now, if you're on the unit circle, which y'all talked about the unit circle in pre-cal, right? Okay. So we have 0 over there at normal, regular old 0. Then we had, what goes on top? Very good. Pi halves. And then what's over here? Pi. And then down here? 3 pi halves. And then finally, 2 pi. Okay. All right. So that's our unit circle. So if we were to like turn this whole thing into a circle, right? If I'm going 180 degrees around the circle, that means I'm starting from this position and I'm going to this position. Then how many pi radians did I go through? 1 pi radian. And if I complete the circle, then I went 2 pi radians. So that's what we're getting right here. 2 pi radians is equal to the full 360 degrees. Okay? All right. Important things that we need to be aware of and not accidentally write incorrectly on our assignments. Lowercase r stands for radius. Okay? Rads stands for radians. Do not write an R for radians as an abbreviation because I'll think you mean the radius and then I'll have to mark it wrong. What? No. Yeah. No, I have not. All right. Good deal. All right. So let's work some practice questions. Garrett, this answers your question. This is what you would see on a quiz or test. Okay. Question is, convert 58.0 degrees into radians. Okay. So we're going to use dimensional analysis. All right. So we're going to put our 58.0 degrees over 1. What unit has to go on bottom? Degrees. How many degrees?
180.
Okay, you could use 180 or you can use 360. Shivam has decided to use 180. All right, so what goes on top? Pi radians. Very good. Okay, so all you have to do is say 58 divided by 180 and then multiply that by pi. Now, listen to me. Here's where you're going to accidentally get it wrong. If you type into your calculator 3.14 or 3.14159, you're going to get it wrong. You need to use the actual pi button on your calculator or you will get this wrong.
Wait, do you not want it in a fraction form?
No, I want an actual decimal number. Yeah, you need to push the pi button. We would use 2 pi instead of just pi. It'd be 360 degrees equals 2 pi radians. This is just half right here. Okay, Adam? Yeah, sig fig. We want 3 sig figs here. 1 point. Radians, very good. Okay, 1.01 radians. Okay, let's do the next one. We want to change 342 degrees into radians. So y'all do that, and then when you've got it, raise your hand. What's your question? You're going to do 58.0 degrees times pi, and you need to actually use the pi button, and then hit enter. And then when you're done with that, divide by 180 and hit enter again. And with 3 sig figs, that's what you should get. Okay? So, but right now, we're doing this number 2, the 342 degrees into radians. Okay? I'll call on one of y'all in just a minute.
360 with 2 radians.
360 is 2 pi radians.
Oh. Okay, gotcha. Yeah, I got that. Oh, dang it.
All right. Okay, technically. Okay, Graham, tell us what you got for number 2, please. Okay, Graham says 5.97 radians. Raise your hand if that's what you got too. Excellent. Okay. All right, and then the last one is going the other direction, and I just noticed a typo. This should say 5 pi third radians into degrees. Okay, so change that into degrees. 5 pi third radians into degrees. Now, you should probably group your pi term in parentheses, especially if it's in the denominator. If you're using 2 pi equals 360 instead of pi equals 180, then down here you would have 2 pi in the denominator. You must put that in parentheses. Otherwise, your calculator is going to divide by 2. Then it will divide again by pi instead of dividing by the quantity 2 pi. Okay?
Or you can cancel the pi. Yep. So then you got 360.
Okay, so raise your hand when you have the answer. Let's see, Garrett.
300 decimal.
Fantastic. 300 degrees. Perfect. That's it, boy. Okay.
You said if you do, make the dot prominent so you can see it. So on questions like this where we're giving the radius first, will you give us the amount of
Yeah. Typically, we should just do 3, I think. We'll just stick with 3.
On everything? Or we're supposed to do angles and 360 anyway.
Yeah. What's up?
So why do we do
Okay.
yeah.
Thank you. All right, let's move on. Shh. Okay, so let's describe the linear distance that a stopper will travel over time. All right, so I'm going to kind of make myself this little arc here to the best of my ability. All right, so there's the stopper at its first position. Here it is at its second position. We've got this angle theta, which would change over time. Both of those are the radius. The radius would not change. The distance from position 1 to position 2 is going to be called S. Okay? S is the arc length. The arc length is a linear distance. Okay? So we have a boxed equation here for arc length. S equals R times theta. Remember, I said if we're going from a linear or translational system to a polar system, it's going to be an R times an angle, right? So the linear distance, S, is equal to R times theta. So on the left-hand side of that equation, linear stuff. On the right-hand side of that equation, polar stuff. When you use that equation, it has to be with radians, okay? So when you plug in a number for theta, you can't plug in like 360 degrees. You're going to have to plug in 2 pi radians in that place, okay? So always use radians with this equation to get it right. Adam? Yes, this will be given to you on any quiz or test.
So when we get the answer, would it be meters?
Yeah, Other questions? All right. Nice. Does everybody have everything on this screen written? All right, let's move on. Okay, so what is the arc length when an object moves through a full circle? This will be the last question today. What do you think that's called? What's the arc length when you move through the full circle? One full revolution. Circumference. Who said that? You did. All right, it is the circumference, okay? Okay, the circumference is a special situation of the arc length equation, okay? Circumference was equal to 2 pi r, right? Okay, so again, the 2 pi right there in that equation, that's theta in terms of radians, right? We plugged in 2 pi radians and multiplied it by r. So circumference is r times theta. It's just the theta has to be 2 pi because we went through the full circle. Does that make sense to everybody? If you don't go through the full circle, then you would use your arc length formula and plug in what angle you actually did go through. No, that is not a box. All right, bye-bye. Y'all have a great week.